Day 18 of 365, and today's strings are going to humble you. Here's the trap. An interviewer asks, are these two strings anagrams? You sort both, compare, done. It passes every test. Then they smile and say, cool. Now what if each string is 10 million characters? Suddenly your login sort is too slow, and you realize you never actually understood strings. You treated them as just arrays of characters. Today we fix that, because almost every hard string problem is one of three patterns wearing a disguise. First pattern, strings are not always cheap to change. In Java and Python, strings are immutable. So when you write result plus equals word inside a loop, you're not appending. You're allocating a brand new string every iteration and copying everything over. That's O in superscript 2, hiding in one innocent line. The fix is a mutable buffer, string builder in Java, or building a list and calling .join in Python. Senior engineers catch this in code review instantly. Know why it's quadratic, and you've already cleared a common screening filter. Second, let's beat that anagram problem properly. Forget sorting. Both strings are just lowercase letters. Then a string is really a frequency contract. Make one integer array of size 26. Walk the first string and increment counts. Walk the second and decrement. If every bucket lands back at 0, they're anagrams. O in time, O1 space, since 26 never grows. You could use a hash map, but for a fixed alphabet the plain array wins on constant factors. No hashing, no boxing, just raw index math. Recognizing this is secretly a frequency problem is the whole skill. Now the payoff. New question. Find every starting position where an anagram of pattern P appears inside text T. Recounting from scratch at each index is O, n times m, wasteful. Instead, slide a window the width of P across T. Each step, add the new character on the right, drop the character on the left, and check if the window's frequency matches the patterns. You reuse almost all the work from the previous position. That's the sliding window. Stop rescanning, start updating. One pass, O, n, and it generalizes to a huge family of substring problems. Take the classic, longest substring without repeating characters. 2 pointers, left and right, both starting at the front. Expand right and record each character in a scene map. The moment you hit a duplicate, shrink from the left until the duplicate's gone. The window between the pointers is always valid, and the largest width you ever see is your answer. Brute force checks every substring in O in superscript 2. The window does it in O, n, because each pointer only ever moves forward, never backward, never rescans. There's a sharper version of this for minimum window problems. Find the smallest substring of T containing all characters of P. The trick is a have versus need counter. Need is how many distinct characters you must cover. Have is how many you currently satisfy. Expand right until have equals need. Now the window is valid. Then greedily shrink left to make it as tight as possible before moving on. You never re-examine a character more than twice. That have versus need pattern shows up constantly, so drill it until it's automatic. And this isn't interview theater, it's how real systems work. A spam filter token matches messages against known bad patterns using exactly this frequency and window logic. Autocomplete leans on prefix indexing, the same prefix table idea behind KMP pattern matching, which finds every occurrence in O, n plus m, instead of O, n times m. Log deduplication hashes normalized strings to collapse millions of near-identical lines. Strings as frequency maps and sliding windows is the bridge from a coding puzzle to actual system architecture. So here's your mental model. A string isn't a sequence you loop over. It's a frequency contract or a window over a stream. Watch out for immutable concat blowing up to O in superscript 2. Reach for a count array on fixed alphabets. Slide a window instead of rescanning. Get these 3 reflexes and hard string problems. Start looking familiar. Day 18 done. Key takeaway. Stop thinking characters, start thinking patterns. Subscribe for day 19.
you.